All right, today we're tackling a massive crack in our understanding of the universe. I'm talking about a problem so big it actually breaks Einstein's greatest theory. The problem? Infinity. But what's really exciting is we're going to explore a pretty radical new idea that might just fix it. A universe that might have had no beginning and maybe no end. So let's just jump right in. Where does our best description of the universe, our fundamental understanding of gravity, just completely, utterly fall apart? Well, the answer is kind of weird. It's both a when and a where. First up, the when, the very beginning of time. The Big Bang. The problem is, our theories predict that the whole universe started as this single point of infinite density and infinite temperature. A place where the math just, it breaks. It gives us nonsense. And the where? That would be at the heart of every single black hole. Yeah, you heard that right. General relativity tells us that at the center of a black hole, there's another one of these points of infinite density, a spot where space-time itself is just crushed out of existence. So these 2 points of failure, they have a name, singularities, and they are the absolute core of what we're calling Einstein's infinity problem. They are the exact spots where his beautiful theory of gravity just completely short circuits. Okay, so what is a space-time singularity, really? Well, think of gravity as the bending or curving of space and time, right? A singularity is a point where that curve just goes to infinity. It's not just a law of gravity, it's a mathematical black hole where all the laws of physics that we know and love just stop. They cease to apply.
And the consequences of that? They're pretty wild. At a singularity, the tidal forces would become infinite, literally tearing everything apart. Space-time itself becomes, incomplete. Imagine you're walking along a path, and the path just ends. Poof, gone. It's a literal dead end in reality. And this is why most physicists are pretty sure singularities aren't actually real. They're more like a big flashing sign that our theory is missing something really, really important.
The physicists behind the theory we're looking at today put it really simply. They say that space-time singularities signal the breakdown of classical general relativity. It's almost like the theory itself is crying out for help, telling us, hey, you need a new idea for these crazy extreme places in the universe. So what is this new idea? Well, what if the universe has its own built-in braking system? A theory of self-regulating gravity designed to stop these runaway infinities right in their tracks. The core idea is actually super elegant. It's this: what if, when the curvature of space-time gets way too intense, some kind of natural mechanism just kicks in and stops it? Think of it like a cosmic safety valve, or a thermostat that prevents things from getting infinitely hot. It's a built-in off switch for infinity. And this chart, it shows the difference perfectly. With general relativity, that bar for curvature just shoots off the top right to infinity. But in this new theory, look at that. It's capped. There's a maximum possible curvature. Gravity gets insanely strong, for sure, but it never, ever becomes infinite. There's a hard ceiling. So how does it do this? It's all about something called negative feedback. Basically, the theory is built so that the intense curvature itself creates a kind of pushback. The more space-time tries to curve, the more resistance it generates. It dynamically stops itself from collapsing into a singularity. It's a self-correcting system. Now, think about this. If you get rid of that first singularity, the one at the beginning of time, you get rid of the Big Bang as we know it. And that leads to the first huge implication of this theory: a totally new origin story for our entire universe. And the change it's profound. General relativity gives us this incredibly violent point-like beginning from an infinite singularity. But this new theory, it swaps that out for something much calmer, a smooth, non-singular big bounce. So what does a bounce actually mean? This timeline lays it out. Instead of a beginning from absolute nothing, this idea suggests our universe might have emerged from a previous contracting one. Imagine that old universe collapsing down, reaching a point of maximum but still finite density, and then it just smoothly bounces back out, transitioning into the expanding universe we see all around us today. But okay, this theory isn't just about rewriting the beginning of time. Oh no. It also completely rewrites what happens inside a black hole. It fundamentally changes what lies beyond that point of no return, the event horizon. And the difference here, is just as mind-blowing. General relativity, it predicts a crushing singularity that just obliterates everything, all information gone forever. This theory, on the other hand, predicts a stable core made of pure spacetime, something called a de Sitter core. You can kind of think of it as a region of super high but stable pressure, almost like a tiny self-contained universe tucked away inside, with intense but finite gravity. So what would that mean for, say, an astronaut falling in? Well, it means their journey doesn't just end. After you cross the event horizon, yeah, you'd feel some powerful tidal forces, but they'd be finite, and you'd eventually arrive at this stable core, a real place in spacetime, not just a point where you get annihilated. Okay, this all sounds really cool, I know. But is it just a neat mathematical idea? Nope, not at all. This is a real, honest-to-goodness scientific theory. And that means two things. One, it has to match up with everything we already know. And two, it has to make new predictions that we can actually go out and test in the real world. And one of the most compelling things about this particular theory is just how well it behaves. I mean, it perfectly matches general relativity in all the places we've tested it, like right here in our solar system. It doesn't cook up any weird, unstable particles. Physicists call those ghosts. And it gets the big stuff right, like predicting that gravitational waves travel at the speed of light. So it passes all the first really important checks with flying colors. So, the million-dollar question, how can we actually prove it's right or wrong? Well, the theory makes some very specific testable predictions. For one, it says that the leftover gravitational waves from a big bounce would have a slightly different fingerprint than those from a Big Bang. It also predicts we should see tiny, measurable differences in the way gravity works right up close to massive black holes. And the best part? These are real signals our telescopes and detectors can actually hunt for. And that brings us to one last, really big idea. By getting rid of the singularity, this theory also gets rid of the very place where information was supposed to be destroyed inside a black hole. And that, well, that opens up a really tantalizing possibility. If this new picture of gravity is correct, could it also be the key to finally solving the famous black hole information paradox? Now that is a question for the next great frontier of physics.